I hope you have seen my previous videos on chemistry and carbon compounds. In this video, I will discuss polymers and plastics. The carbon chains that have been introduced, the alkanes, alkenes, and alkynes, can all serve as basis material for creating plastics and polymers. The goal of discussing synthetic polymers is to end up with a better understanding of long carbon chains so that we can transition more easily into the long carbon chain natural polymers that form the building blocks of life. The oldest plastics are the celluloids. In 1855, Alexander Parker developed Parker-Seen, the first man-made plastic by treating cotton-based cellulose with nitric acid to produce nitrocellulose. In raw form, the nitrocellulose is explosive gun cotton. Gun cotton has up to 6 times the explosive power of black powder and was used to fire artillery shells during the American Civil War. In 1867, John Wellesley Hyatt improved upon Parker-Seen by processing nitrocellulose with camphor to develop a plastic he called celluloid. Hyatt's first use of celluloid was to make synthetic billiard balls, a replacement for expensive elephant ivory that had been used previously as the material for making billiard balls and piano keys. Hyatt's celluloid became the base plastic for the celluloid film used in the motion picture industry for most of the 20th century. The first fully synthetic plastic, bakelite, was developed in 1907 by the Belgian-American chemist Leo Baekeland. Bakelite has been used to make electrical insulators, the exterior cases for household appliances, and a wide range of other items such as jewelry and toys. Throughout the 20th century until today, chemists and engineers have been developing new plastics and finding new uses for plastics. These plastics are based on a carbon chain molecule, the polymer. The most basic link in a polymer is called the mer. A mer is not a complete molecule, but a section or single link in long-chain polymer. The mer of a polymer consists of carbon atoms singly bonded to a pair of hydrogen atoms, leaving the 2 remaining valence electrons of the carbon atom free to bond with other atoms. The brackets indicate the bonds extend to other atoms. A polymer is just a chain of mers. The mer is derived from a simple complete molecule called a monomer. The simplest monomer molecule is ethylene, C2H4. In ethylene, the hydrogen atoms are single bonded, while the carbon atoms are joined by a double bond. As the double bond between the carbon atoms in the ethylene molecule is weak, it does not take much energy to coax the double bond to break into a single bond. This will allow each carbon atom to be free to bond with another atom. The step required to break the double bond and begin the polymerization is called initiation. The polymers formed will be of different lengths depending on the termination step. A vessel full of ethylene molecules will readily chain together to form polymer chains of varying lengths. The chain of ethylene monomers will form the polymer chain called polyethylene. The little subscript N after the bracket indicates how long the polyethylene chain is. N could be a number in the hundreds or thousands. Polyethylene keeps the suffix -ene, even though it has no double bonds, as a reminder of the monomers, ethylene, from which it was formed. Polyethylene is used to make plastic wrap and plastic bottles, among other things. After polyethylene, the second most common polymer is polypropylene or polypropene, formed from the propene monomer. Propylene is ethylene with a methyl group, CH3, substituted for one of the hydrogens. Again, the double bond is broken into a single bond to leave each carbon free to bond with another carbon atom. The mer for polypropylene is shown. The polypropylene mer form might be sufficient, or we could extend the mer out a few more iterations to show more clearly the repeating sequence for polypropylene. A third important polymer is polyvinyl chloride, PVC. PVC is used in a wide variety of products from plumbing to old-style vinyl phonograph records. The mer for PVC is the same as polypropylene, except the substitution is a simple chlorine Cl atom instead of a methyl group, CH3. So, the mer for polyvinyl chloride is shown. In the polymer Teflon, or polytetrafluoroethylene, PTFE, fluorine atoms are substituted for all the hydrogen atoms. In Teflon, the fluorine atoms are so satisfied with their bond to the carbon atom that they don't interact with much else. This makes Teflon a great coating for non-stick cookware. The van der Waals bonds that normally form between food and whatever it is next to just don't form against Teflon. or are so weak as to prevent food from sticking against the smallest force attempting to remove the food. The mer for Teflon has the molecular form shown. Teflon was discovered by accident in 1938 by Roy J. Plunkett at a DuPont company lab. Plunkett was attempting to develop a new chlorofluorocarbon refrigerant gas using tetrafluoroethylene, C2F4, gas. As he was releasing the TFE gas from its pressure bottle, the gas stopped flowing before the bottle was empty. Plunkett wondered why the gas stopped flowing. He noted the bottle weighed more than an empty bottle should weigh. Plunkett was curious enough to saw open the pressure bottle to see what happened to his TFE gas. What he saw was a waxy white substance that was oddly slippery. The iron pressure bottle had acted as a catalyst to polymerize the TFE gas into PTFE. The PTFE was patented in 1941. PTFE was used to coat valves and seals for the Manhattan Project. PTFE was trademarked as Teflon in 1945. Another useful polymer is polystyrene. In solid form, polystyrene is hard and brittle. It can be used to make protective packaging such as CD jewel cases. When puffed up with air bubbles, polystyrene becomes the excellent thermal insulator or flotation material styrofoam. In the styrene monomer, benzene C6H6, or a phenyl group C6H5, is substituted in place of one hydrogen in ethylene, C2H6. With every odd hydrogen replaced in the carbon chain, the polystyrene mer has the form shown. Polymers can be made with several combinations of monomers to form a copolymer that has many of the good characteristics of component polymers. ABS plastic or acrylonitrile butadiene styrene is a copolymer of acrylonitrile, butadiene, and styrene monomers that are linked together in alternating fashion. ABS is usually made by polymerizing styrene and acrylonitrile in the presence of polybutadiene. The styrene gives ABS plastic its shiny surface, hardness, and rigidity. The acrylonitrile makes ABS chemically resistant and fatigue-resistant, as well as harder and more rigid than styrene alone. The butadiene gives ABS rubbery and ductile characteristics that gives ABS toughness even at low temperatures. The monomers for ABS are as shown. In the chemical diagrams, the carbon atoms are assumed at nodes and hydrogen atoms are assumed as necessary to complete the 4 valence bonds of carbon. Another copolymer is polyurethane. Polyurethane is not a single copolymer type, but a whole class of copolymers where the monomers are linked by a urethane or carbamate group, an H2COOH. The carbamate or urethane structure that links other chemicals R1, R2, R3 is shown. Shown is a reaction of D-isocyan at linked to diol by a urethane to form a polyurethane mer. Polyurethanes have a wide variety of properties, and so can be used to produce a wide variety of products including foams, coatings, adhesives, electrical insulators, and flexible fabrics such as lycra and spandex. The polymers can take on many forms: high density, low density, crystalline, and amorphous. The polymers can form thermoplastics and thermoset plastics. The polymers can also be cross-linked between carbon chains to form materials and fabrics of different strengths. For example, high-density polyethylene, HDPE, has a crystalline structure of closely linked parallel polymer chains that give it a high tensile strength that make it good for making water bottles, plumbing, and synthetic lumber. Low-density polyethylene has a non-crystalline, amorphous branching structure that cause it to have lower tensile strength to make it ideal for products that should be flexible, including toys, plastic wraps, juice containers, snap-on lids, and flexible binding materials such as six-pack rings. Both types of polyethylene are thermoplastics, meaning they can be melted down and remolded into other products. Other plastics such as polyester, polyurethane, ABS plastics are thermoset plastics that cannot be melted down and reformed once they are cured into their final form. Polymers can be used to make fabric for clothing and furniture upholstery. Polymers can be drawn into synthetic fibers that can then be woven as synthetic fabrics such as rayon, nylon, polyester, and Kevlar. The oldest of the synthetic fabrics is rayon. In 1857, Swiss chemist Matthias Schweizer is credited for developing a copper ammonia solution, CuNH3 sub 4 H2O sub 2, OH sub 2, that has become known as Schweizer's reagent. Schweizer used his reagent to dissolve cotton, linen, cellulose, and silk. Schweizer found he could extrude the solution as fiber. In the 1890s, German chemist Max Framrey and Austrian chemist Johann Urban found they could use Schweizer's reagent on cellulose to produce fibers that could be used as light bulb filaments. In 1899, Framrey and Urban started the Vereinigte Glanzstofffabriken AG factory in Oberbruck, Germany, where they used copper ammonia rayon to weave textiles. In 1904, the J.P. Bremberg AG acquired the Vereinigte Glanzstofffabriken AG company and began to use copper ammonia rayon to produce artificial silk. Copper ammonia methods of producing rayon are toxic and so are falling out of favor. A skeletal diagram of dissolving cellulose with Schweizer's reagent is shown. In 1894, English chemists Charles Frederick Cross, Edward John Bevan, and Clayton Beadle patented an artificial silk created by their viscose method. Viscose rayon is made in a process that starts with a cellulose reaction with a strong base, NaOH. The solution is then treated with carbon disulfide, CS2, to create a xanth-8. The xanth-8 can be drawn out of the solution or extruded as a rayon fiber. The xanth-8 solution is very viscous, hence the name viscose for the material. The name rayon was adopted in the United States in 1924. Viscose is the name of the precursor liquid to both rayon fabric and to cellophane. In Europe, viscose is still in use for the viscose rayon fabric. Another important synthetic fabric is nylon. In 1926, the DuPont company started a synthetic fabric research group led by Wallace Carruthers. By 1935, Wallace Carruthers had developed nylon 66. After being inspired by Carruthers, Paul Schlack at IG Farben developed nylon 6 in 1935. Nylon was commercialized for use in toothbrush bristles in 1938. The first nylon stockings were introduced in 1939. Nylon 6 starts out as 6-aminohexanoic acid, which is modified to become the caprolactam ring. Breaking a single bond unfolds the nylon 6 monomer. To manufacture nylon 66, add adipic acid to hexamethyl-enadiamine to get the nylon 66 monomer. Nylon 66 chains cross-link with a hydrogen bond whenever an NH group lines up with a CO group. This cross-linking prevents the polymer chains from slipping past one another and so result in stronger material. Other nylon isomers have similar cross-linking. Nylon 66 is abrasion-resistant, holds its color and resists breaking down in sunlight, and is used in pleated clothing. Nylon 6 is also abrasion-resistant, dyes easily but fades easily, and is used for clothes, seatbelts, and carpets. Another popular synthetic fabric is polyester. Polyester is a whole family of polymers, the most common being polyethylene terephthalate or PET. The carboxylate ester functional group RCOOR' is the polymer chain. Linking group where the R's represent the rest of the monomer. The carboxylate ester is shown. Natural polyesters are made by plants to coat their leaves and by bees of genus called Aedes, which they secrete and use to coat the walls of their incubation cells. The DuPont Company's Synthetic Fiber Research Group, formed in 1926 under Wallace Carruthers, discovered polyester about the same time as nylon, during the 1927 to 1935 time period. The DuPont Group ignored polyester to focus on nylon. In 1939, a group of British chemists, led by J.R. Winfield, revisited Carruthers' work on polyester, and in 1941 created a polyester fiber they called terylene. In 1946, the DuPont Company bought up the rights to polyester and developed the polyester material they called Dacron. Polyester was introduced to the public in 1951 as wrinkle-resistant clothing. The most common form of polyester, polyethylene terephthalate, or PET, has the mer shown. The PET mer is expanded to show its groupings. A host of synthetic fabrics were invented and improved throughout the 20th century, and many new ones are still being developed in the 21st century. A significant development in synthetic fabrics was Kevlar, the brand name for polyparaphenylene terephthalamide. Kevlar was developed at DuPont in 1965 by Stephanie Kwolek. She was looking for material to strengthen car tires. The polymers she had been working with at the time formed liquid crystals while still in solution. the solution would normally be discarded. Kwolik persuaded lab technician Charles Smullen to test fibers drawn from her solution, and was amazed to find that the fiber did not break at tensions that would certainly break nylon. She and her supervisor immediately recognized the importance of her discovery. Kevlar is not important as clothing fabric. Kevlar is significant as a specialized fabric because Kevlar fibers have a tensile strength above 3,000 megapascals. This high tensile strength exceeds that of most steels in a material that is much lighter than steel. Kevlar has a wide range of applications where high tensile strength is required, including belts for machinery, as a replacement for steel reinforcing belts in car tires, and for uses in bulletproof vests and body armor. There have been many more forms of Kevlar developed since Stephanie Kwolik's discovery in 1965. The monomer for Kevlar is synthesized by reacting 1,4-phenyline diamine with terephthalonyl chloride. Note the phenyl groups in both reactants and the amino NH2 and carbonyl groups CO that hold the monomer together. Kevlar fibers are so strong because of the cross-link hydrogen bonds between the amino groups NH2 and carbonyl groups CO in parallel chains of Kevlar fibers. The frequency of the hydrogen bond crosslinks in Kevlar are much greater than the crosslinks of other polymer fibers such as polyester or nylon. It is the density of crosslinks that give Kevlar its strength. Also, when the phenyl aromatics of sheets of Kevlar are stacked, there are more van der Waals bonds that form between the planes that give Kevlar even more strength. Below is a diagram showing the crosslinking in a Kevlar lattice. Note one Kevlar monomer is highlighted in bold line and font. From the stories of the discoveries of both Teflon and Kevlar, we can see that new discoveries in chemistry often take the form of accidents and incidents that only a very curious chemist would investigate and only a very astute chemist would spot as something important. This statement is not to take away from the long hours of hard work that chemists perform with often toxic or explosive chemicals. My point is that chemistry is not very predictable. A chemist may understand that mixing two chemicals will cause a reaction. If the chemist has never seen the reaction before, the chemist can only guess at the product of that reaction, and the properties of the product are equally unpredictable. Who would guess that the product of an alkali metal and a halogen gas is a crystalline salt? It is only in hindsight that a chemist can look back and fully understand the reaction, and why the new product has the properties it has. For complex reactions, the results are unpredictable. This is a limitation of chemistry. There may be computer algorithms developed in the future that may help with prediction, but only a real experiment will prove out the results, and relying on computers may cause chemists to miss the lucky accidents that produce such great products as Teflon and Kevlar.
Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.